Alright, so in this section we're going to cover the net change theorem. And this is a very important theorem, which is an application of the fundamental theorem of calculus part 2. So the goals of this section are, so first I'm going to remind you of the integration formulas, and a comprehensive list of all of those formulas, at least the basic ones, is found in a table on page 489 in our textbook. And we're going to explain the net change theorem, which is the central theorem of the section. And then later on we're going to use this net change theorem in applications. And later on at the very end we're going to talk about integrals of odd and even functions. Now, before I start saying something more about the net change theorem, let me remind you that this section is basically about interpretations and applications of FTC2. Okay, so FTC2 is basically what we need in this section. So let me first remind you about the fundamental theorem of calculus part 2. So recall that FTC2 says the following. So if you take the integral from a to b of f prime x dx, this is equal to f of x from a to b. So this means the net change in f. Now this is exactly, also later I'm going to say this is exactly the statement of the net change theorem, but it's stated in a different language. Now before we get to that theorem, let me give you one example of how you can actually use this theorem. So for example, if you have to integrate from negative e to negative 1 the function 1 over x dx, then according to this FTC2 we have, remember, the most general antiderivative of 1 over x is ln of absolute value of x. So you first plug in negative 1, so ln of absolute value of negative 1 minus ln of absolute value of negative e. So this is equal to ln 1 minus ln e. Remember, ln 1 is 0 and ln e is 1. So this is equal to negative 1. Okay, so this means that we'll have to know at least the basic list of antiderivatives and indefinite integrals, or indefinite integrals, which is listed in page 489 in our textbook. So this means that, so we need to know or review, because we've already done this, the list of basic, let me say basic antiderivatives, or we can say indefinite integrals. And if you want, you can look at page 489 for the table that I was talking about. Okay, so for example, you also need to combine them. So for example, if you find the integral, let's say the integral of secant squared x plus 1 over 1 plus x squared minus e to the power of x, then the most general antiderivative of this, or you can also say this indefinite integral, is equal to, remember that the antiderivative of secant squared is tangent, then the antiderivative of 1 over 1 plus x squared is tangent inverse, or arctangent. And then for e to the x you have, so this should be minus, for e to the x you have e to the x again, so plus the constant c. Okay, or for example, if you want to use the power rule, if you have a question like the integral of x to the power of 3/5 minus 6x dx, this is equal to, remember, if you use the power rule for integrals, you have x to the power of 3/5 plus 1 over 3/5 plus 1 minus 6x squared over 2 plus c, and so on. Okay, So you should be able to at least solve questions of this sort. All right, so now let me state the net change theorem. So the net change theorem says the following. All right, so let me first state this. So this says that the integral of the rate of change of a quantity f on a closed interval, let's say a comma b. Now, of course, we're assuming that f is a nice function. It has nice properties. So the integral of a rate of change of a quantity, I should say the rate of change here, sorry about that, of the rate of change of a quantity, f on a closed interval a comma b equals, this is important, equals the net change of the quantity f on the closed interval a comma b. So in other words, this means the following. This means that the integral of the derivative from a to b is equal to f of b minus f of a. So this means that the rate of change, which is here, so this is, let's say, rate of change of f, of change of f, this is equal to the net change of f. Okay? So the integral of the rate of change of f is equal to the net change of f. That's the statement of the theorem. And this has some very important applications. So let me first highlight this and I'll move on. So this has some very important applications like the following. So here I'm going to draw a table now, and we're going to actually discuss some of the applications. So let me just say applications. All right. So now let's take some examples and try to read those examples using this language of the net change theorem. So let me just say, read the net change theorem using the following examples. Okay, so I have three quantities. I have f, then I have f prime, and then I have fb minus fa. So for example, the first thing I want to talk about is the following. So go back here. So the first example is position. So if f is position, excuse me, then the rate of change of position is velocity. So this means that the integral of the velocity function, which is the rate of change of position, is equal to the net change in position. So this should be now the net change in position. So again, the integral of the rate of change of position is equal to the net change in position. Or in other words, the integral of velocity is equal to the net change in position, which we also call the displacement of the object. Okay, or another application could be the following. So if you have, for example, population is your quantity f, then the growth rate of the population is the derivative of the population function. So let me just say the growth rate of population. And the integral of the growth rate of the population is the net change in population. And so on. So let me give you two more. So for example, if you have that F is the volume of water, then the derivative of the volume is the rate of the water flow. Then the integral of the rate of water flow is the net change in the volume of the water. Okay, of water. And so on. So one more example maybe. So if you have that your quantity is the mass of a rod, then the derivative in physics, the derivative of the mass of a rod, if it's a linear, is called the linear density. And the net change in the mass is called the mass of the segment. And so on, okay? So you can take your favorite quantity, take its derivative and whatever it means physically, and then the integral of that derivative is just the net change in the quantity. Okay, so we're basically going to work mostly with position and velocity, and maybe also with population and population growth. So the other ones are, for example, number 4 is not really very relevant to our course, but this is just to give you an example of what all these three quantities mean in the net change theorem. Here. All right, so let me give the first example here. So the first example is the following. Again, these are applications. So you have a particle that moves along a line. Okay, and this has velocity given by the following: t squared minus t minus 6. Let's say this is measured in meters per second. Okay, so the first question is, find the displacement of this particle during the time interval from 1 to 4 seconds. So A, find the displacement of this particle during the time interval let's say t is between 1 and 4 seconds. Now the displacement is the net change in position, so we're going to use that. So recall that displacement is equal to the net change in position. So this would be, let me just say this as the position at 4 minus position at 1. But now according to our theorem, this should equal the integral from 1 to 4 of the velocity function. Okay, so it means that we need to find the integral of the velocity function from 1 to 4. So let's do that. All right, so the integral is equal to the integral from 1 to 4. So the velocity function is t squared minus t minus 6 dt. So this is equal to, remember that we have to use the power rule here, so t cubed over 3 minus t squared over 2 minus 6t, and we have to plug in 1 and 4 and then find the difference. So we have that this is equal to 4 cubed over 3 minus 4 squared over 2 minus 6 times 4 minus, you plug in 1, so 1 cubed over 3 minus 1 squared over 2 minus 6. And if you do this calculation, you'll find negative 9 over 2. And displacement can be negative, okay, because motion has direction. So if the direction is positive in one way, then the displacement of this particle is in the other way. Okay, so let's do part B. So part B asks us to find the distance traveled during this time period. Okay, so B, find the distance traveled. So this is the total distance traveled during this time period. Okay, so now we don't have to find the displacement here. We have to now do something more specific. Now all motion should be treated as positive, so we have to find the integral of the absolute value of the velocity function. So the distance traveled is equal to the integral from 1 to 4 of the absolute value of Vt. Okay, this is very important here, dt. So to be able to find this integral, we first have to find where this function v is positive and where it's negative. Whenever it's positive, we just find the integral, and whenever it's negative, you have to multiply that integral by -1. All right, so let me do that first. So remember, the velocity function is t squared minus t minus 6. So if you want to find the zeros of this, because we're going to sketch the graph, you factor this as t minus 3, t plus 2. Okay, so if you set this equal to 0, then you have that t is equal to 3, or t is equal to -2. So if you sketch the graph, let me do that. Make this a little straight. Maybe that's better. Okay, so we have following. So here is -2. Let's say here is 3, -2, and 3. So if you sketch this graph, it's more or less like this. Okay. Let's say here is 4. Now we have to find the integral from 1, let's say 1 is somewhere here, from 1 to 4. So basically we want to find this area here and this area here, but I have to treat both of those areas as being positive. So let me highlight this very quickly. So we want this area here, okay, and then this other area here, and we have to treat both of those areas as positive. So this means that our integral from 1 to 4 of absolute value of Vt dt should be written as first the integral from 1 to 3 of minus Vt dt plus the integral from 3 to 4 of just v dt. And the reason for this minus here is because this area here, if you do this just by evaluating the integral is going to be negative. To make it positive, you multiply the function by -1. Okay, so let's do this. So this is equal to now minus, so remember the antiderivative of v as we wrote up here. So this is the antiderivative of v. Okay, this is equal to t cubed over 3 minus t squared over 2 minus 6t from 1 to 3 plus t cubed over 3 minus t squared over 2 minus 6t from 3 to 4. And if you do this calculation, you'll find 61 over 6, which is approximately 10.17 meters. Okay, so this has to be positive. If by any chance you find a negative number here, then it's probably wrong. Okay, I mean, it's definitely wrong, not probably wrong. All right, let's move on. Let's do one more application. Now we're going to do a more relevant application to what we're experiencing right now. So we're going to do a population problem. So let P be the number of people who have contracted a virus after T weeks. A virus after 3 weeks. Sorry, after T weeks, not 3 weeks. T weeks. Okay? If the rate of change of this population with the virus, so if the rate of change of P this is the growth rate basically. So this is, maybe I should say the growth rate. Is given by, so this is, of course, we're going to have an exponential model. So this is exponential and given by the following. So I have P prime t is equal to 2 times 3 to the power of t. This is just some simple model. Then find the net change in the number of people who have contracted the virus in the first 12 weeks. Find the net change in the number of people in the population who have contracted the virus in the first 12 weeks. Okay, so according to the net change theorem, the net change in this population, and let's say in P on the interval 0, 12 is equal to P12 minus P0, which is equal to also, according to our theorem, the integral from 0 to 12 of P prime t dt. So let's do this. So this is equal to the integral from 0 to 12 2 times e to the 3 to the power of t dt. So this is equal to, you can take the 2 outside, so this 2 can go outside here in front of the integral. And the antiderivative of 3 to the power of t, remember, is 3 to the power of t over ln 3. So you get 2 times 3 to the power of t over ln 3 from 0 to 12. Okay, so this is equal to 2 times 3 to the power of 12 over ln 3 minus 2 times 3 to the power of 0 over ln 3. So this is basically 2 over ln 3 times 3 to the power of 12 minus 1. And if you evaluate this using a calculator, this is approximately 967,475 people. So this means that with this rate of change, about, again, 967,475 people will get the virus in 12 weeks. And 12 weeks is about 3 months, right? So in 3 months, about 1 million people will get infected if this is, say, if this is the rate of change of the population with the virus, which is given by this formula here. Okay, so I hope that's clear. Now let's move on and talk about even and odd functions and their integrals. So let me remind you of even and odd functions first. So let me start on a new page. So remember, even and odd functions. These functions have the following properties. So an even function is basically a function which is symmetric with respect to the y-axis, and odd functions are symmetric with respect to the origin. So let me write each of them individually. So first I'm going to write about even and then odd functions. So even and then odd. Okay, so a function is even if the following happens. If f of negative x is equal to f of x, and f is odd if f of negative x is equal to negative f of x. Of course, you have other types of symmetries as well, but these are some of the basic types of symmetries. And if you draw a picture of an even function or an odd function, you get something like the following. So let me first draw an even function. I hope I can do that because I have to be symmetric with respect to the y-axis. So I need the same axis on the right because I'm going to draw also an odd function. All right. So if you want to have an even function, then you have something like this. So for example, if you have something like this on the left, you have to have that on the right as well. Okay, so this should be symmetric with respect to the y-axis. Okay, so it has to be a reflection. So this is some sort of an even function. So let me put some ornaments here. So let's say this is interval negative a comma a. Okay, and this is an even function. So this is symmetric with respect to the y-axis. Okay. And if you have an odd function, then it has to be symmetric with respect to the origin. So I'll try to be creative here, so let me extend this x a little bit. So I'll try to do this. Let's say I have okay, so whatever we have on this quadrant in this picture, you should reflect it to have this side of the quadrant. Okay, so this is symmetrical with respect to the origin. All right, so again here we have, let's say, the interval negative a comma a. Okay, so this is an odd function. This is symmetric with respect to the origin. All right, so let me tell you about the rules of integration now. So maybe you can guess from here that if you have an even function like this one here, and integrate this on the interval negative a comma a, then this area here is the same as this area here. So what you can do is you can integrate from 0 to a and then multiply by 2. And on the other side, if you integrate from negative a to a, an odd function, this area is the same as this area, but they have negative opposite signs. So this area is, this area is negative, this area is positive, so they just cancel each other out. So that's the statement for the integrals of even and odd functions. So let me just say rules for integrals. Okay. All right, so the first rule is that if f is even, then the integral from negative a to a of f is the same as twice the integral from 0 to a of f. Okay, and if you have an odd function, if f is odd, then the integral from negative a to a of f is equal to 0. Okay, so again, if you have that a function is even, then the integral can be replaced by twice the integral from 0 to a. Of course, you need to have a symmetric interval from negative a to a. Okay, if you have some other interval, you cannot do this. And then if you have an odd function, then the integral is just 0. Of course, again, if you have a symmetric interval. So let me give you two quick examples. So the first example is the following. Let's say I have the integral from negative 1 to 1 of 5x to the power of 10 plus 3. Now this function is even, so this integral can be written as twice the integral from 0 to 1 of 5x to the power of 10 plus 3. Okay, so this is much easier. So this is equal to twice, you have 5x to the power of 11 over 11 plus 3x from 0 to 1. Again, if you plug in 0, you get 0. If you plug in 1, you just get 1 for x. So this is equal to 2 times 5 over 11 plus 3. Okay, this is if you have an even function. If you have an odd function, then you have the following. Let's say you have the integral from negative pi over 3 to pi over 3 of sine x dx. Now remember, sine x is an odd function, as we did in long calc 1. So this should equal just 0. Okay, and if you want to check, then if you integrate sine x, this is equal to negative cosine x from negative pi over 3 to pi over 3. So this is equal to negative cosine of pi over 3 plus cosine of negative pi over 3, and this is going to be just 0. So this is negative 1 over 2 plus 1 over 2, so this is 0. Okay, this is if you want to check. But you don't really need to do this, because you can just say that if you're integrating an odd function, like sine x, on the symmetric interval from negative pi over 3 to pi over 3, then you should get just 0. So you don't have to do this. Alright, so that's it about section 5.4.